from other electrons due to their mutual negative charge, but it also attracts the positive ions that make up the rigid lattice of the metal. This attraction distorts the ion lattice, moving the ions slightly towards the electron, increasing the positive charge density of the lattice in the vicinity. This positive charge density attracts other electrons. At long distances, this attraction between electrons due to the displaced ions can overcome the electron's repulsion and cause them to join. Two electrons, when joined together in this way, are called a Cooper pair. And the positively charged region of the atomic lattice is part of what is called a phonon. A collective motion of multiple ions with the same frequency are called phonons. Phonons are important for conducting heat and sound through solids, but for our purposes, they are important in understanding superconductivity. If the temperature of the material is low enough, the Cooper pair remains together because it does not have enough energy to break apart. This pair can then be treated as a single particle. When two electrons come together in this way, their half spins interact in such a way that together they form an integer spin. In other words, they start behaving like bosons instead of fermions. They are no longer subject to the Pauli exclusion principle. What happens now is that since an arbitrary many bosons can fit into the same low energy state, the collection of Cooper pairs starts acting like one entity or unit. This state, when a bunch of bosons cooled to low temperatures occupy the lowest quantum ground state, is called a Bose-Einstein condensate. They act like one bosonic electron, all at the same low energy state. And it's negatively charged because it is made up of electrons that are negatively charged. So this means it can conduct electricity. Normally, when an electron collides with an atom and scatters, it loses some energy by going to a lower energy state than before it collided. This energy is lost to the lattice of the metal. But with Cooper pairs, there's no lower energy state for it to go to. There is no quantum state that these bosons can occupy that is lower because they are already at their lowest energy state. So no energy is lost because they can't lose any more energy. The lack of interaction of the Cooper pairs with the atoms effectively results in no resistance to the flow of electrons, and the material becomes a superconductor. The interaction of the electrons in a Cooper pairing is very weak, so it typically only happens at very low temperatures. As the temperature gets above the critical temperature, the Cooper pairs get disrupted because there's enough energy to break.
Here's how they do it. They apply a strong electric field on one side of the atom. Normally, the nucleus sits at the center, while the electron's probability cloud is spread evenly around it. But once the electric field is switched on, the negative electron cloud gets pulled slightly in the direction of the positive side of the field, while the heavy positively charged nucleus is pulled just a little in the opposite direction. This makes the atom slightly tilted or polarized. One side now has a denser electron cloud, and the other side has a thinner one. Because of this distortion, the potential energy landscape of the atom, what scientists call the potential barrier, becomes uneven. On the side where the electron cloud is pulled, the barrier becomes thinner and lower. The electron's wave function, which normally fades out smoothly at the edges, now stretches a bit farther in that direction, reaching into the region beyond the barrier. Tunneling in Josephson junctions is used to store, manipulate, and read quantum information, forming the foundation of modern superconducting quantum computers. The three scientists were awarded the Nobel Prize for building these special circuits. These circuits allow electric current to behave in strange quantum ways. They showed that even a circuit made of millions of electrons, large enough to be seen or handled, can still show quantum tunneling, a phenomenon once thought to exist only in the microscopic world. Their experiments proved that such circuits can absorb and emit energy in fixed, discrete amounts, just like real atoms do. By controlling these effects, they were able to create artificial atoms, man-made versions of nature's building blocks. These artificial atoms are now used to build quantum computers, ultra-sensitive sensors, and other advanced quantum technologies that could transform